Hi everyone, in this video I'm going to take you through modeling of catheters as a common example of continuum robots. The model we use here, which fit well to modeling of structures similar to catheters, is called virtual discrete jointed robot model. Here you can see an electrophysiology catheters, which are briefly called EP catheters. EP catheters are specialized medical devices used in cardiac electrophysiology studies and procedures to diagnose and treat arrhythmias. These catheters are designed to navigate between the cardiovascular system and reach a specific location in the heart where they can measure electrical signals, deliver energy for ablation, or pace the heart. These catheters are one of the strong applications of continuum robots in the field of minimally invasive surgery. We find many research focused on modeling and control of different types of them. So in this presentation, I'm going to go over a method well fit to modeling of catheters and similar structures. The method is named virtual discrete jointed robot model. The virtual discrete jointed robot model is a method used for simplifying modeling of continuum robots. Instead of dealing with the continuous structure of continuum robots directly, this approach breaks the robot model into some discrete segments connected by some virtual joints. This approach allows us to capture compliance and flexibility of continuum robots and at the same time benefit from the straightforward computational method used for traditional rigid body robots. Catheters can move in three main ways. They can slide forward or backward in translational motion. We call this motion insertion motion. They can twist around their proximal end or they can bend at their distal end. Alright, now let's go to the modeling. On the left you can see a bended catheter. We'll start by adding a prismatic joint to capture the insertion motion of the robot and a revolute joint to simulate the twist motion and another revolute joint to take care of the bending. And here we have the three main motions of insertion, twist, and bending. But as you can see, bending and unbending of the catheter corresponds to changes in the distance between the proximal and the distal end of the catheter. So to capture different aspects of motions of the catheter, we need to add some corrector joints. So let's just start by adding a prismatic joint to um, reflect the changes in the distance between the proximal and the distal end of the catheter, and also one revolute joint at the distal end of the bending section of the catheter to take care of the bending angle. Now let's assign coordinate frames. On the right, you can see the rules I follow in assigning frames. We start by ZI axis. ZI aligns joint axis I. This axis defines the rotational or translational movement specific to that joint. Then we have origin OI. For origin OI, locate the origin OI where the common normal to ZI minus 1 and axis ZI intersect ZI axis. If ZI intersects ZI minus 1, locate OI at the intersection, and if they're parallel, locate OI in any convenient point along ZI. And finally, XI, establish XI along the common normal between ZI minus 1 and ZI, passing through the origin OI, or in the direction normal to the plane formed by ZI minus 1 and ZI if the two axes intersect. So let us start by Z1. Z1 along the translational motion of joint 1, and the same for Z2, Z3, Z4, Z5, and Z6. For O1, we can set origin anywhere along axis Z1. And for O2, since Z1 and Z2 are parallel, it can go to any convenient point along Z2. We select this point here. And since Z2 and Z3 intersect, ZO3 goes to the intersection point. And since Z3 and Z4 also intersect, so O4 goes to the intersection of these two axes, and the same for O5 and O6. Now that we assigned coordinate frames, we can fill out the Deneva-Tarchenberg table. Here you can see what convention I used to measure theta, alpha, A, and D parameters. Following these definitions, the field table can obtain at what you see here. Our independent variables here are D1, theta 2, and theta 3. Later, we will obtain d4 and theta 5 as functions of other parameters. Also, d7 is a constant value reflecting the offset between the last coordinate frame and the robot end effector. All right, now let's go to the dependencies. There is a coupling between theta 3 and d4 that I'm going to cover in this slide. On the left, you can see a bended catheter, and on the right, you can see a catheter bended half through. As you see, bending or unbending the bending section corresponds to the change in the distance between the proximal and distal end of the bending section of the catheter. We're gonna see how these changes can relate to other parameters. Mm, L L here is the length of the banding section. We assume the radius of the banding section at the shown moment is r. From triangle algebra, we know that the cosine of theta 3 equals to half of d4 divided by the hypotenuse length. Also, we knew that the circumference of the arc, which we know equals to L. Here you see L divided by 2 as I'm capturing, uh, as I'm applying the rule for this, for half of this angle here. So the length of the circumference of the arc also will be L divided by 2. So we know that the circumference of the arc, which equals to L divided by 2, equals to radius multiplied by the angle between the two radii. Now these two gives us a coupling between d4 and theta 3. Also, from the convention we set earlier to measure thetas, we know that theta 5 equals to the angle between the angles between x5 and x6 about z5. From corresponding angles theorem, we know that this equals to minus theta 3. Now that we have the Deneva-Tarchenberg parameters and the coupling between the independent and dependent parameters, we can obtain the forward kinematics of structures like catheters, as you can see here. And this is the end of obtaining the forward kinematics for this structure. Thank you for being with me today. Don't forget to like, follow, and subscribe for more videos.